Welcome back to thermodynamic class. I am Dr. Ravi, working as assistant professor in the Department of Pharmaceutical Engineering, BVR at Narsapur. Today, Unit 3, that is solution properties. So, objective of this unit is to understand, to determine the thermodynamic liquid properties. So, after completion of this unit, student able to understand how to determine the thermodynamic liquid properties. So when you map the this unit outcome with the program outcomes, we can see PO1 engineering knowledge. It will give and fulfill the 100% for engineering knowledge, and PO2 also 100%. Like in a PO12, it is a lifelong learning. This unit will help you in the lifelong learning. Next, content of Unit 3. This is the content. First, partial molar properties we discuss. In that, what is the partial molar property? What is the physical meaning of that? Second, when determine how many determining methods for partial molar properties, and the next partial molar property for solution. So next one, chemical potential. What is the chemical potential? First, in that, what is the effect of temperature on chemical potential? Next, what is the effect of pressure on chemical potential? After that, next content is the concept of fugacity. Next, concept of activity and their calculations, ideal and non-ideal solutions, Gibbs-Duham's equation, property change of mixing, and excess properties. With these, third unit will be completed. Next, first one, introduction. Introduction regarding the solution properties. So we know when the compound in a pure state, for example, it is having some volume, and when it is added in the mixture, we thought generally the mixture total volume is equal to sum of the volumes of the pure state, but that is not correct. It is not correct, because when any compound which is in a pure state, pure means a single state, the molar volume, for example, that is X, but that when it in that case, when it is added in the mixture, because of the molecular interactions and attraction and repulsion forces, because of that, the volume, for example, that the X volume will be decreased or increased based on the different conditions. Means whenever any compound which is in a pure state, the molar properties are not equal to the when they are in a mixture state. So that is about the introduction about this. Means, so here we are going to know the when any compound, when it is in a mixture state, what is the property of that. So that property is called partial molar property. Partial molar property, the property of any compound in a mixture. So generally that is denoted with the molar M in a general words, because it can amplify any property. It could be volume, it could be other property, and any property. So generally it is denoted with the M. So the partial molar property is equal to dou means here change in total molar property with respect to the change in number of moles of that compound. So this is, here we can see that change in total molar property with respect to the change in number of moles. Means when to a mixture, when particular number of moles are added to that mixture, Then because of change in number of moles of that compound, what is the change in total molar property, that with respect to the change in number of moles, that is equal to the partial molar property of that particular compound. So here mi bar is equal to the partial molar property of a compound compound I in the solution. And here n is the total number of moles. M is the molar property of solution. So M is the molar property of solution, and total number of moles into molar property of solution is equal to total number of moles. That's the reason partial molar property of any compound in a mixture is equal to dou Nm by dou Ni at a constant temperature, constant pressure, Nj not equal to I. Means here at constant temperature and constant pressure, Nj not equal to I means apart from, because here we are doing what is the partial molar property of a compound with respect to the change in number of moles of that particular compound. In that case, remaining all other compound moles are kept constant. Temperature kept constant, pressure kept constant, and all other compounds in that mixture moles are kept constant. So that we can write in other words dou Mt by dou Ni at constant temperature, constant pressure, Nj not equal to I. So here the M is the molar property of solution. Ni is the number of moles of compound. Here total N is equal to summation of all summation of moles of all compounds. Next, Mt is equal to total value of any extensive thermodynamic property of a solution, means total molar property, nothing else. T is the temperature, here P is the pressure, Nj not equal to I is, I already said, the number of moles of all components in the solution other than the number of moles of I are kept constant. Except I, remaining all other compounds and moles are kept constant. Means only I compound moles are changing. With respect to the I compound moles are changing, what is the total molar property changing? That ratio is equal to partial molar property of that compound in that mixture. What is the physical meaning of this? So we in the introduction I already said for example any compound in a pure state, single state, it is having some particular volume. So consider like a 1 ml volume it is occupying. That 1 ml volume, when it is added in the to particular mixture, in that case, that 1 ml may not be the 1 ml, it may be greater than or less than the 1 ml. So that is this is the meaning of partial molar property. So what is the property of any compound in that mixture? Means because the property is changing, the property of any compound changing in the mixture. Okay. So to understand this, for example, we can see already. For example, one mole of water add to the huge volume of water. Then that 1 mole of water is occupied volume is increased by 18 into 10 power minus 6 meter cube. Here the water volume in that huge water, the volume is what in this 1 ml volume in a pure state, how much it is occupied. Compared to that, when it is in a mixture, when in the 1 mole of water added to the mixture, then 18 to 10 power minus 6 meter cube volume is increased. In other words, like in the same way, the 1 ml of water is added to the huge volume of ethanol. Then the volume, this 1 ml of water volume is increased by 14 into 10 power minus 6 meter cube. We can see that. So same 1 ml of water added to the huge volume of water, in parallelly, same 1 ml of water added to huge volume of ethanol. When they are added, the volume is in the first case volume is increased 18 into 10 power minus 6 meter cube, but in the second case the volume is increased 14 into 10 power minus 6 meter cube. So means the volume the change of property is changing with respect to the mixture because of the molecular interactions between those mixture. So this is the physical meaning of partial molar property. Next, how to determine this partial molar property? There are generally three methods are there. First one is the analytical method, graphical method, and tangent intercept method. The analytical method means using the formula. That formula mi bar is equal to dou mt by dou ni at a constant temperature, pressure, nj not equal to I. Using that formula, the partial molar property of a compound can be determined. This method is known as analytical method. Second one is the graphical method. Using the graph means the draw the graph between the particular compound which only one compound moles are changing. That is, for example, consider I compound, that is 1, for example. So the in general words, draw the graph between the total molar property with respect to the Ni. What is the compound you are interested? So that compound continuously with the change, adding the number of moles to that mixture, what is the total molar property changing? When you draw the graph between this total molar property and that change of I compound number of moles, then we got the graph like this. So to that graph you draw a tangent at your interest. To that tangent, determine a slope. That is, slope is dou mt by, because dou mt by slope is the dou mt by dou ni at constant temperature, pressure, nj not equal to I. So that is the partial molar property of that compound. Otherwise, here for example, if you want in a particular case, for example, first compound, change of first compound number of moles with respect to the total number of moles. You draw the graph. When you draw the graph, you will get some parabolic curve. To that curve, draw a tangent. So to that tangent, determine the slope. That slope determines what is the partial molar property of compound 1. In the same way, second compound, draw the total molar property y-axis, x-axis N2 moles with changing the N2 moles. In the same way, and from there, from the slope, we can determine the partial molar property of the second compound in the mixture. So this is called graphical method. Next one is the tangent intercept method. This method is especially for binary mixtures. So in that case, draw graph between the mole fraction of any compound. For you take the x1, first compound mole fractions with initially the mole fraction here x1 is equal to 0, here x1 is equal to 1. So with the change of mole fraction of a compound 1 from 0 to 1, and what is the in y-axis molar property of the solution m. Now when you draw the graph between the I already said this is for binary mixtures. So when you draw the graph between the molar property of a solution with respect to the mole fraction of a compound 1, so then we get the graph one parabolic curve. To that parabolic curve, draw a tangent where you want to at what particular mole fraction, if you want to determine what is the partial molar property on that for example, here any particular this is your interest at At this mole fraction, you want to determine what is the partial molar property of compound 1. Then to this, and just perpendicularly draw a point at that point, draw a tangent and extend the tangent. It will intersect the x-axis and y-axis on both sides. So this is represent, that is A, here that is A, and that is okay. So the AC that segment and BD segment. Now at x is equal to here at origin, x1 is equal to 0 and x2 is equal to 1. And x2 is equal to 1, the partial molar property is equal to AC. Here x is equal to 1 means x2 is equal to 0. Here x2 is equal to 0. Now the mole fraction, first compound mole fraction and x1 is equal to 1, the partial molar property is equal to BD, the length of the segment. So at particular, for your interest, that is the at that mole fraction partial molar property is the slope of that. Okay, dou m by dou x1. So that in that way, the advantage of this tangent intercept method, we can determine two compounds. Initially, in a previous method only, if the change of moles of particular compound, that's the first compound, then we can only determine what is the partial molar property of that compound in that mixture. But here, tangent intercept method, for binary mixture, we can determine for two compounds, when they are in a pure state, what is the partial molar property of that compound, and at your interest, at that mole fraction, what is the partial molar property of that compound in that mixture. So that is the advantage of tangent intercept method. Next one, partial molar property of solution. Up to now we have seen what is the partial molar property. Now what is the physical meaning of that? So third one is the how many methods are there? What are the different methods to determine the partial molar property? Now, what is the total partial molar property of the solution? How to determine that? So that is the total molar property of the solution is equal to m. It is a function of temperature, pressure, number of moles of each compound in the solution. Okay. So what is the change of the total molar property? That is DMT. What is the change of that total molar property? That is equal to the only with the temperature, what is the change of partial molar property, plus only with the pressure, what is the change of partial molar property, plus only with the one compound, first compound, change of first compound with respect to that, what is the change of partial molar property, like so on. So that is a summation of them. Okay, that's the reason. So it can be written as dmt is equal to dou mt by dou p at constant temperature and total number of mole. dp means with respect to only pressure. With respect to the only pressure, what is the change in remaining all kept constant, temperature and number of all the moles of all the compounds kept constant. Okay, so that's the reason. Because of that, we need to take the partial derivation. That is dou mt by dou p at a constant temperature and a number of moles, total number of mole into dp, plus dou mt by dou t at because we are deriving with respect to temperature, so we need to keep pressure and total number of moles are kept constant dt, plus dou mt by dou n1 we are deriving with respect to the change in first compound number of moles. So constant temperature, constant pressure, N2, N3, N4 are kept constant, so on. So dN1 plus dou mt by dou N2, constant temperature, T pressure, N1 comma N3 comma N4, so on dN2 plus dou mt by dou N3 at T temperature, pressure N1 comma N2 comma N4, so on dN3 plus so on dou mt by dou Ni T constant temperature, pressure Nj not equal to I dNi, so on. Okay. So this whole thing we can write as summation of dou mt summation of dou mt by dou Ni constant temperature, pressure Nj not equal to I dNi. We can write like this because only summation of this. So that way we have written dmt is equal to dou mt by dou p t comma n dp plus dou mt by dou t at t p comma n dt plus that is the only we have written summation of summation n is equal to 1 to n dou m t by dou ni t p n j not equal to I dni. Okay. Okay, but we know that this one, which one? The mi bar is equal to dou mt by dou ni constant temperature, pressure n j not equal to I. That we know. So okay, so now this is that is mi bar. So substitute that. So dmt. Now what will happen? dmt is equal to dou mt by dou p Tn into dp plus remaining everything is same here. Summation I is equal to 1 to n mi bar into dni. Okay, so that we get. Now at constant temperature and pressure, what will happen at constant temperature and constant pressure? The derivation of temperature is equal to, because this is a constant. The constant, because the derivation of constant is 0. So dt is 0 and dp is 0. Okay. When you substitute that dt, dp and dt, so these two terms will be 0. So now we'll get the dm here because at constant temperature and pressure, this is a dmt at constant temperature pressure. So this term will be 0 and this term will be 0, this term will be 0, and plus we will get this one. So finally we will get the dmt at constant temperature and pressure, that is equal to summation I is equal to summation, this is I is equal. So we got, so now we got that dmt at constant temperature and pressure is equal to summation of I is equal to 1 to n, I is equal to 1 mi bar dni. We got this one. Okay. So expand the above expression. When you expand that, what do you get? When you get, you will get the dmt constant temperature and pressure is equal to m1 bar dn1 plus m2 bar dn2 plus m3 bar dn3 plus so on. We get. Now integrate on both sides. When you integrate on both sides, okay, this is a we'll get. So this integration will be applied to each term. So that's the reason integration of dmt at constant temperature and pressure is equal to integration of m1 bar dn1 plus integration of m2 bar into dn2 plus integration of m3 bar into dn3, so on. So this is we will get that from there. We'll get that when you do the integration, the derivation integration, we'll get that from that the integration of derivation of something. We'll get the mt and the constant temperature pressure is equal to m1 bar into n1 plus m2 bar into n2 plus m3 bar into n3. Okay. So now for both sides, now up for the right hand side, multiply with the number of moles and divide. Then now the what is the division part is there, apply to each term. So each term. So this is indirectly, this is a mole fractions, means we are writing in a mole fraction. For example, the total number of moles, for example 1, then what will happen, that is a m total molar property at constant temperature pressure is equal to summation of first compound partial molar property into mole fraction plus second molar property into mole fraction, that's mole, and the third molar property into that mole fraction, so on. Means the total molar property of a mixture at constant temperature and pressure is equal to summation of each compound partial molar property multiplied with its mole fraction. Okay. So in this way, we can write in terms of moles, in terms of mole fraction. In terms of moles is the m constant temperature and pressure is equal to m1 bar n1 plus m2 bar n2 plus m3 bar n3, so on. That is mt is equal to summation ni into mi bar. Otherwise, in other words, in a mole fraction also we can write from here. So mt at constant temperature and constant temperature pressure is equal to summation of partial molar property of each compound into number of moles of particular compound, or in other words, mt constant temperature pressure is equal to summation of mi bar into xi. So this is the partial molar property of a solution. Our total molar property of a solution is equal to summation of each compound partial molar property in the solution and multiplied with its mole fraction. Next one is the second topic, chemical potential. So what is the chemical potential? So for if take two systems, so I am saying these two systems are in a thermal equilibrium. So what is the meaning of that? The two system temperatures are same. So then means for thermal equilibrium, temperature is the index. Temperature is the index for thermal equilibrium. In the same way, so any mechanical device is not moving because in both sides are two systems are in a pressure, and there are in a equilibrium with the pressure. Means the pressure is the index for mechanical equilibrium. In the same way, chemical potential. What is the in a simple words we want to know, like a temperature is the index for the thermal equilibrium and pressure is the index for mechanical equilibrium. In the same way, chemical potential is the index for chemical equilibrium. If any chemical reaction is there, the reactants are converting into the products. We are saying this reaction is in a chemical equilibrium. Means what? Reactants chemical potential and products chemical potential both are reached to same. So that's So this means the chemical potential is the index. So means if the chemical potential is same for both reactants and products, then we say that the chemical reaction is reached to chemical equilibrium. Okay. So this is the means what is the chemical equilibrium. So for definition part, it is a change in free energy. The chemical potential is change in free energy with a change in number of moles or particles. Okay. So for example, take the mixture. In that in that mixture 1, 2, 3, 4, 5 like so on, n number of different compounds are there. Okay. In that you added first compound for some particular number of moles of first compound you added. When you add that first compound, some certain number of moles of first compound, when you add to that mixture, there is a change in free energy. So that means with respect to the change of particular compound, what is the change in free energy? That is equal to the chemical potential. Okay, the chemical potential of so it is denoted with the mu. Okay, the change of free energy with respect to the change of number of moles at constant temperature and pressure. In other words, in a mixture, chemical potential of a particular compound is equal to change of total free energy with respect to the change of moles of particular compound at constant temperature, constant pressure, Nj not equal to I. Means other moles are kept to constant. Okay, so you take the beaker. In that 1 to n compounds are there. Now you added, for example, 1 mole of first compound, 1 mole of one compound. We are giving the name is 1. So 1 mole of first compound is added to that mixture. When it is added, there is a change in free energy. Okay, because if that change in the free energy is that change with respect to the change of moles of that particular compound is called that. So chemical potential of that particular compound. Like if it is more, then that particular compound chemical potential is more. Okay. Here GT is the total free energy of a solution. So generally this chemical potential is also is a function of the total free energy, is also function of temperature, pressure and number of moles of a each compound in the mixture. Okay, so that we can write that GT is equal to function of temperature, pressure, N1, N2, N3, so on, Ni, so on. Okay, and what is the change in total free energy? That is dGt is equal to what is the change? What is the change in total free energy? That is equal to with respect to only temperature, what is the change in free energy, plus what is only with respect to only pressure, what is the change in free energy, what with respect to the only each compound, change in each compound moles, what is the change in total free energy, is the summation of them all. Okay, that's the reason dou g T by dou T at constant pressure, number of moles dt, plus dou G T by dou P, constant temperature and number of moles dP, plus dou G T by dou N1 at constant temperature, constant pressure, N2 comma N3, so on, dN1 plus dou G T by dou N2, constant temperature, constant pressure, N1 comma N3 comma so on, so dN2 so on. Okay, so like that. So in the same way we can write this dG T is equal to dou G T by dou T, pressure at constant pressure and number of moles d T, plus dou G T by dou P, constant temperature and number of moles d P. So this we can write as a summation of I is equal to 1 to n dou G T by dou Ni, so d Ni. Okay. So this is dGT is equal to dou G T by dou T, pressure and number of moles dt, plus dou G T by dou P N dP, plus we already know this one is the summation of this one. We already know this one is the mu I. Okay, so summation of I is equal to 1 to n mu I into dNi. Okay, now after this we need to determine the what is the dou G T by dou T, constant pressure and number of moles. What is the dou G T by dou P, this term? We need to determine this term and this term. So to determine this term, we already know the free energy. Gibbs free energy is equal to H minus Ts. From here, the fundamental relationship formula is there. That is we have seen all. So that is dG. That is the fundamental relation from the fundamental property relation for dG is equal to VdP minus S dt. Okay, so this term, now we can write this term for total change. So dGT is equal to Vt dP minus St dt. Now derive this term with respect to the temperature first. Now dou G T by dou T. So pressure is constant and number of moles are constant. So only with the temperature. So this is because this is the Vt is a constant and dP is also constant, because we are doing only with respect to the temperature only. So this term is 0. We will get the only minus St. So now from here we got the dou dGT by dou T constant pressure and number of moles is equal to minus St. From we got 1. Okay. Now next, say this term. Now again derive with the pressure. Now dou G T by dou P at constant temperature and number of moles is equal to P. We are deriving the P, so we'll get the Vt. Okay, this is the these two terms we got. So these two terms substitute in the previous equation. That previous equation is this one. So we need to substitute from here. When you substitute d g t is equal to g. Now we got when you derive with the temperature, we got the minus st dt plus Vt dP plus summation I is equal to 1 to n mu I into dni. So finally we got this one. dgt is equal to minus st dt plus Vt dP plus summation I is equal to 1 to n mu I into di. Okay, this is called fundamental relationship for free energy change. This is for the fundamental relationship for total free energy change. Okay, so here after this, assume at constant temperature, there dt is equal to 0, constant pressure dP is equal to 0. Okay, so now substitute them in the above equation. Now we'll get the dgt is equal to, so this is 0, something into 0, 0, both are 0. We'll get the summation I is equal to 1 to n mu I into dni will get. Okay, so expand this. After this, expand, we will get the dgt is equal to mu1 dn1 plus mu2 dn2 plus so on. Okay. Now integrate both sides. When you integrate the both sides, integration of dgt is equal to integration of mu1 dn1. Now say integration of mu2 dn2 so on. Now gt is equal to mu1 n1 plus mu2 n2 so on. Okay. Now from gt is equal to, now we can write summation of I is equal to 1 to n mu1 n1. For binary mixtures, gt is equal to mu I ni, mu1 n1 plus mu2 n2 for binary mixtures. For binary, okay, so this is at a constant temperature and constant pressure. Okay, so this is about the chemical potential. Okay, so because the chemical potential, the chemical potential what is the chemical total, what is the chemical potential of a compound? So that is because change in a total change in a free energy. So that total change in a free energy is equal to each compound chemical potential in the mixture multiplied with the number of moles. So summation of each compound chemical potential is and multiplied with the number of moles. So that summation is the total free energy, total free energy at constant temperature and pressure. Now, what is the effect of temperature on chemical potential? With changing the temperature, with respect to temperature, what is how the chemical potential is changing? So, to that we already know this one. We already know this expression, mu I is equal to dou G T by dou Ni at constant temperature, pressure, N J not equal to I. We already know this one. Okay. Now, derive this expression with respect to the temperature. So, then dou mu I by dou T, because we are deriving the temperature, pressure and total number of moles are constant. Then what do we get this one? Dou square G T by dou T into dou Ni will get. Okay, dou T into dou Ni. We already know this one from the previous expression, dou Gt by dou T at constant pressure and total number of moles, that is equal minus St, we know. Now derive this expression with number of moles. So then we'll get the dou square Gt by dou T into dou Ni is equal to dou St minus dou St by dou Ni. So because we are doing with the Ni, constant temperature, constant pressure, Nj not equal to I. Okay. So this is this expression. We go. Now, for both are equal. So equate them both sides. So that we'll get the, when you equate them both, we'll get the dou mu I by dou T, constant pressure, number of moles is equal to this one. This minus dou St by dou Ni constant temperature, constant pressure, Nj not equal to I. Okay. So this we can write dou mu I by dou T, constant pressure N is equal to, this is we can write in other words, this is a partial molar property or partial entropy. So that we can write, because it's same as like a mi bar is equal to dou mt by dou Ni constant temperature, constant pressure Nj not equal to I. So same like it is, we can write minus S bar T. Okay. So this is the, what is the effect of temperature and chemical potential is equal to the effect of means with changing the temperature at constant pressure and number of moles of a particular compound, chemical potential is equal to, so finally you get dou mu I by dou T, constant pressure and number of moles is equal to minus Si bar. Means the particular compound chemical potential with respect to change of temperature is equal to that particular compound entropy in that, partial entropy in that mixture. Okay. Next, with the pressure. So same way, we already know mu I is equal to dou G T by dou Ni at constant temperature and constant pressure Nj not equal to I. Okay. So derive this expression with a pressure now, because with respect to pressure, what is the chemical potential, change in chemical potential. So dou mu I by dou P, because we are in pressure, temperature and number of moles, that is dou square G T by dou P into dou Ni. Okay. We already know dou G T by dou P, constant temperature and number of moles is equal to Vt. We already know this. Okay. Now derive this expression with respect to the number of moles of particular compound. So dou G T. Now what will happen? Dou square Gt by dou P into dou Ni is equal to dou Vt by dou Ni, constant temperature, constant pressure, Nj not equal to I. Okay. So this expression and this expression both are same. This term, this one and this one, both are same. So we equate these two expressions. So we will get dou mu I by dou P, constant temperature, number of moles is equal to dou Vt by dou Ni, constant temperature, pressure, Nj not equal to I. Okay. Now in the same way we can write dou mu I by dou P, constant temperature and is equal to, this is, we can write V bar I. Okay. Okay. And the change of with respect to the pressure, change in pressure, with respect to the pressure, the change in chemical potential of a particular compound in a mixture is equal to partial volume of that particular compound. Okay. Next one is the concept of fugacity. Okay. So generally the ideal mixtures, the compound pressure is expressed for ideal mixtures. The compound pressure in that mixture, one particular compound is there, that compound pressure is expressed in terms of pressure only. But for real mixtures or non-ideal mixtures, the compound which is there in the mixture, the compound pressure is expressed in terms of not in a pressure, because in ideal mixtures we said compound pressure is pressure, but non-ideal mixtures are real mixtures, the compound pressure expressed in other thermodynamic property, that is called fugacity, that is denoted with the small f. Okay. So what is the fugacity means? It is the effective pressure of a particular compound in a mixture, in a non-ideal mixture or real mixture. It is a effective pressure of a compound in a non-ideal mixture. Okay. So this fugacity of a particular, so this can be expressed as fugacity of a compound is equal to a mole fraction into pure compound fugacity multiplied with the pure compound fugacity. Means the fugacity of a compound in a mixture and a real mixture is equal to the mole fraction of that compound into when it is in pure state, the fugacity multiplied with the fugacity, and this is for the gases. In liquids, fugacity of a compound is equal to mole fraction into Fi bar. Okay. Here is the xi bar, xi comma yi are the mole fractions of a particular compound I in a liquid phase and gas phase. Okay, so the ratio of fugacity F, the ratio of fugacity and pressure is this ratio is called fugacity coefficient, that is pi. Okay, for ideal means this fugacity coefficient says how much any particular compound is deviating from the any compound in a mixture is deviating from the ideal behavior. Here ideal behavior means, so generally in ideal behavior means any compound in a mixture there are no interaction between the compounds. And when you say, for example, any compound is behaving as ideal means there are no interaction between those compounds. Because of that, when it is in a pure state, what are the properties it is having? Because they don't have any interaction in a mixture state also. Okay, the same properties it is going to have. But in a real state, it is not like that, because in a because of the interaction, the properties are changing. Okay, so this fugacity coefficient says how much any particular compound is deviating from the ideals. Okay, so that's the reason. So fugacity for ideal cases, this pi is equal to 1. Non-ideal cases, the pi is not equal to 1. This is for ideal mixtures. So non-ideal mixtures. Okay. Now because of that, F is equal to pi p. For here pi p, here F is equal to p. Okay. In a ideal mixture, the compound concentration is expressed in terms of concentration. But in a non-ideal mixture, the compound concentration is expressed in terms of in other property. It is in a thermodynamics, they introduce one more new property, that is called activity. In a real mixture, the compound concentration is expressed in terms of activity. So this is represented with a small a. So definition for this activity is equal to the effective concentration of a compound in a non-ideal mixture. Okay. So generally in ideal mixtures, the activity is equal to mole fractions. For gases, AI is equal to YI. For liquids, ideal liquids, AI is equal to XI, mole fractions. But non-ideal mixtures, the one more coefficient, that activity coefficient is introduced, that is AI is equal to pi I into YI, non-ideal gases. Next, AI is equal to gamma I XI for non-ideal liquids. Okay, these pi I and gamma I, pi I bar and gamma I are the activity coefficient for gases and liquids respectively.
Like, share and subscribe. Hit the bell icon for more updates.